So finishing off the notes for section 3-1, we're going to be looking at repeated zeros and also what the shapes of the graphs look like near those zeros. So the main thing is looking at what it looks like at the zero. A zero also is known as an x-intercept. So in this first example, the first thing you're going to be asked to do is find the zeros. And the zeros are the x-intercepts. So I have zeros here, here, and here. There's 3 zeros. So I would say one of the zeros would be at x equals -2. I'd have one of the zeros at x equals 0. And then I'd have another 0 at x equals 3. So if you look at the original expression right here, if I set each of these factors equal to 0, I could go ahead and get each of the solutions that I have right here. The one thing that you might notice is this one, this 0, it's twice. It's x minus 3 and then it's a factor 2 times. Notice what it looks like at 3. If you have a squared, it kind of bounces off at that 0 right there. It kind of looks like a parabola. What's the degree of this polynomial? Well, all you have to do is multiply all the x's together. So this would be x squared times another x would be x cubed times another x would be x to the 4th. So this is a degree 4 polynomial. Also notice how many directions it has. 1, 2, 3, and 4. You can also look at it that way. So the main thing is it looks like a parabola at the 0 where you have the squared. The other ones, they just slice through and there's just 1 there. In this next example, we have x times x plus 2 times x minus 3 cubed. First thing, what are the zeros? So you can set each of these factors equal to 0. And you would get x equals 0, you would get x equals -2, and you get x equals 3. Notice the graph. Here's -2, here's 0, and here's +3 right here. So notice what happens at the one that's to the 3rd power. It kind of looks like a cubic. So it slices through. It doesn't bounce or look like a quadratic when it was to the 4th, but it slices through and looks kind of like a cube. The ones that all have one factor just slice through like this, and then don't bounce off or bend at the 0. And in this example, we have each of our zeros at x equals 1 right here, and we have -2 right here. And if you were to set each of these equal to 0 right here and here, you could get 1 and -2, the 0 straight from the graph. The degree, all you do is add the exponents. The degree is 7. And here's the big thing, is notice when it's cubed, what happens at the 0. At 1, it looks like a cube. And then when it's an even power, what it does is it bounces off. This is a little bit flatter, because to the 4th power looks like this. So x to the 4th kind of looks flatter. Not really like a parabola, but flatter than a parabola. So then it bounces off and kind of looks like a 4th power at that root. So we're going to summarize our findings that we just came up with. So we're going to talk about the shape of a graph near a 0 with a repeated factor. So starting off, we're going to talk about if it's an odd power. Alright, so if m, which is our exponent right here, is an odd power, meaning 1, 3, 5, 7, or so on, what's going to happen is our graph will slice through at +c, because +c is what will make that 0. And if it's 3, 5, 7, it will either bend like that, or let's say this is C, it can bend this way. In either case, it slices through the 0. So in case 2, if the exponent is even, so let's say my factor is x minus c to the m power. So here's your exponent right here. So if you have 2, 4, 6, 8, and so on, when you go ahead and make your graph, what's going to happen is at +c now, what makes that 0, your graph is going to bounce, and it'll either be flatter depending on the power, but it'll basically bounce off of the 0 and not slice through. So it either can be on that side of C depending on the orientation, or it can bounce like this, but it will not go completely through that 0. So now that we have all the tools to actually graph, we're going to be graphing polynomials with, sorry about that, that was my water bottle. We're going to be graphing polynomials without a calculator, and here are the 3 steps. Step 1 is to find the zeros. Step 2 is to use the leading coefficient to determine the end behavior of the graph. So is it ending up on the right or down on the right side? So the last step is to determine the shape of the graph from its degree. So if it's degree 4, you'll have 4 turns or 4 directions, along with how the graph bends or bounces off the x-axis at the repeated zeros. So remember, if it was an even degree, it would bounce off, and then if it was an odd, it would slice through but kind of bend at the 0. So in this example, you're asked to sketch a graph of p of x equals x minus 1 squared. So notice that it's squared, so we're going to have a little bounce on the x-axis, x minus 2 and x minus 5 cubed, and this one's odd. So first thing you have to do is determine the degree. So remember, if you were to multiply all this out, you'd have an x cubed. You get the x cubed from that times this other x, so now we have x to the 4th times another x squared because that's squared. So basically just add up all the exponents. You get 2, 3, 4, 5, 6. So it looks like we have the degree is 6. So if I were to do a little sketch over here, I would have either something that looks like this, 1, 2, 3, 4, 5, 6, or I would have something that looked like this, 1, 2, 3, 4, 5, 6. I just have to figure out which one is going to be the right orientation. And what we do is we look out in front. So in this case, notice how I have no negative out in front. It's positive. So that means it's going to end up going positive on the right. And then the last thing I have to do is look at the zeros. So let's go ahead and find the zeros next. Alright, so I'm going to go ahead and set each of these factors equal to 0. So I'm going to have a 0 at 1, I'm going to have a 0 at 2, and I'm also going to have a 0 at 5. So I'm going to make a little note right here. The 1 at 5 is a triple 0. And the 1 at 2, or the 1 at 1 is a double 0. So I'm going to put double. So anything that's even is going to look like this at the 0, and anything that's odd is going to look like this at the 0. So then I'm going to go ahead and make my sketch now. So I'm going to mark down my x-intercepts or my zeros, 1, 2, 3, 4, and 5. And then I'm going to put my little marks on it because this is where it's going to cross, 1, 2, and 5. And then I have to make it look something similar to this. It's got to have 5 directions. So at 1, it's going to be a double direction. Now I actually like to work backwards because I know it's going to be ending up. So at 5, I have to make it look like this. It's going to be a triple. So I'm going to do this. Alright, so that counts as 1, 2, 3 directions. And notice how I'm ending up going upward. And then at 2, it is a odd degree, so it's going to slice through. And then at 1, it's going to turn and bend and go up something like this because of the double 0. Anytime it's a single, it slices through. And then if it's 3, 5, 7, or larger, it's going to bend at the 0. So that would be my graph. In this example, first thing we're going to do is to determine the degree. So adding up the number of x's, you have an x squared here times another x, so it's x cubed, or the degree would be 3. Next thing is the orientation. Notice that it's negative. So that means if I have a negative orientation, that it's going to end up going left and have 3 directions. So I know it's going to end up going down on the right hand side. So it's going to go down. And then the zeros are what make each factor equal to 0. So I have one at negative 3 and positive 3. and the one at -3 is a double zero because of that little squared on it. So that means whenever it's double, it's going to bounce off the 0. So now I can go ahead and make my sketch. So I'm going to put -3 and +3 right here. I'm going to go ahead and put on my marks. Use a different color here. And then I know that it has to go down on the right because of this negative sign, and it has to have 3 directions, and then it has to bounce at -3. So I am going to work backwards. I know it has to end up going down. This one right here is a single 0, so it's just going to slice through, and then it has to bounce off of that one, and then it looks like that. So anytime it's a single 0, there's just one, it slices through. Anytime it's a double or a quadruple, so 2, 4, 6, it'll bounce. And then if it's like 3, 5, or 7, it will kind of bend at the 0. So the last thing is the local extrema of the polynomials, and we've already done this. These are just the local minima and maxima of the graph. So if I were to do a little sketch, and let's say your polynomial was degree 3, you would have your local max, and this would be your local minima. We've already done this in the last 2 chapters. So there is one theorem, and the theorem states if p of x is degree n, then there is at most n minus 1 local extrema. So basically in the example I drew here, we have the degree 1, 2, and 3. That means there's 1 less than 3, or 2, 1, 2 local extrema. So in this example, you're supposed to determine the number of local extrema of this polynomial. So the big thing is you need to know what the degree is. It's the highest exponent, so the degree is 4. So you know there's at most 1 less than the degree. So there's at most 3 local extrema. Now to figure out exactly what they are, you'd need to create a graph. So in this graph, you'll notice that you have a local min here, a local max there, and another local min. So there's your 3. So then to get more specific, you would say 2 mins and 1 max. And to calculate them, they didn't ask you to calculate them. You could just do calc min and max and look at the y coordinate. Okay, that's it, and I will see you guys tomorrow.